Hi everyone! Today I'm presenting my work on few-shot learning graph multi-trajectory evolution network for forecasting multimodal baby connectivity development from a baseline time point. This work has been done at Basira Lab by myself, Ella Sadik, Ahmed Nerdi, with the collaboration of Dr. Gang Li, Dr. Wei Li Lin, Professor Jingang Shen, and supervised by Dr. Muhammad Ali Mahjoub and Dr. Islam Reki. Given a baseline brain graph derived from a specific modality, such as functional connectivity, and acquired at specific time points, how to predict its multi-trajectory graph evolution, where each trajectory represents a different brain modality, such as structural and morphological connectivity. There are few studies on brain graph evolution prediction. However, all these methods predict unitrajectory evolution where brain graphs are derived from a single modality. Therefore, they do not generalize to multi-trajectory graph evolution prediction. Furthermore, they overlook the preservation of topological properties of the original brain graph, and they require many training brain graphs to boost model learning, which reduces its learning capacity where only a few training samples exist. To overcome these limitations, we propose GmTE Net, a teacher-student framework trained for jointly predicting multiple trajectories of infant brain graphs from a single neonatal observation. Each baby sample S is represented by a set of brain graph multi-trajectories, and each represents a brain modality such as functional connectivity. Since each brain graph is encoded in a symmetric matrix, we vectorize the off-diagonal upper triangular part and stack the resulted vectors in a matrix VNITI for each brain modality. In that way, we eliminate redundancy of edge weights of brain connectivities. We repeat the same process for each time point to obtain a tensor TM representing a single trajectory. By doing so, we create a multi-trajectory representation of our training set. We all know that training a deep learning framework using limited data is feasible, but it never outperforms same models with large data. So, we propose the teacher-student scheme, where we first train a teacher network using a limited number of brain graphs so that it learns the pure connectivity patterns. Second, we freeze the teacher model and train a student network on simulated data such that the network can generalize to different types of brain connectors. In that way, the student model benefits from the few-shot learning of the teacher model. To enforce the teacher model to capture the high-order representation of the input brain graphs, we propose a global topology loss. And to further ensure a node property preservation in the predicted brain graph, we further propose a local topology-aware distillation loss to transfer the local graph knowledge from the teacher to the student. We design both teacher and student models as two graph autoencoders, each composed of an encoder E aiming to learn the latent representations from the baseline brain graph, and a set of graph trajectory decoders. Basically, a set of GCN layers are cascaded n-times, where each predicts a brain feature matrix at a different time point. The first GCN layer might play a scaling role in a case of resolution difference between initial and target domains. In such scenario, it maps the brain graph from the initial resolution domain to the follow-up brain graph dimension. We evaluated our framework on 11 developing infant subjects. Each is represented by two brain graphs derived from two different brain parcellations. We compared against two ablated methods and its two variants using mean absolute error, eigenvector, and stage rank centrality. Our model, GmTE Net star, is ranked first best when predicting the morphological brain graph trajectory, and second best following GmTE Net variant when evaluated on functional brain graphs. We introduced in this work the first teacher-student framework tailored for predicting baby brain graph multi-trajectory evolution over time from a single neonatal observation. Our framework circumvents the learning on the few brain graphs as we train the teacher network solely on few shots and the student network on simulated brain graphs. And in our future work, we will incorporate a domain alignment module into each decoder of our network so that we reduce the domain fracture resulting in the distribution difference across brain modalities. Thank you for your attention, and feel free to check our recent review paper on GNNs in network neuroscience covering recent GNN architectures for brain connectivity integration, classification, super-resolution, and more. You can also visit the GitHub repo of the paper. For more, please visit us at basira-lab.com.